We are looking at a robot controlled entirely by a browser, and you might be wondering if this is just another hype video about cloud AI. The reality is far more interesting and far more demanding. We are witnessing the collapse of the cloud dependency model that has dominated artificial intelligence for the last decade. By the end of this explanation, you will understand exactly how a single browser tab can now orchestrate physical hardware without sending a single byte of data to a server, and why this shift fundamentally changes the engineering landscape for robotics. For years, the narrative has been that running large language models requires massive cloud infrastructure. The assumption is that you need expensive GPUs, constant internet connectivity, and a backend server to handle the heavy lifting of inference. This model works fine for simple chatbots, but it fails catastrophically when you need to control physical machinery. If your internet connection drops, the robot stops. If the cloud provider experiences an outage, your entire operation halts. There is also the critical issue of latency. Sending data to a server, waiting for processing, and sending it back introduces a delay that is unacceptable for real-time control loops. The engineering burden of managing these external dependencies has kept advanced robotics locked behind high-cost barriers. The paradigm shift begins with a technology called Transformers.js. This library allows us to take models designed for massive data centers and run them directly inside the browser. It leverages WebGPU, a standard that gives web applications direct access to the graphics processing unit. This is not a simulation. The browser is using the actual silicon on your machine to perform matrix multiplication. When we load a quantized version of the Gemma 4 model, which contains billions of parameters, the system loads it into the GPU memory and runs the inference entirely within a web worker. This isolates the heavy computation from the main thread, ensuring the user interface remains responsive while the AI thinks. This architecture eliminates the cold start overhead that previously made browser-based language models impractical. Because the model is loaded once and kept in memory, subsequent queries happen in sub-second latency. The system does not need to establish a network connection, authenticate an API key, or wait for a server queue. The reasoning happens locally. This allows the browser to act as the sole orchestrator. It can analyze sensor data, make decisions, and execute commands without ever leaving the device. The security implications are profound because there is no data exfiltration. The robot's sensory input never leaves the local environment. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the interface layer. We are not just running text generation, we are using a system called WebSerial to communicate with physical hardware. This protocol allows the browser to open a direct serial connection to a device, bypassing the operating system's traditional driver stack. In this specific setup, the browser sends commands to a Reachy mini robot. The robot receives these instructions, moves its joints, and sends back telemetry data. The entire loop is closed within the client-side application. The AI reads the data, decides on the next move, and sends the command back through the serial port. No external API gateway is involved. However, we must address a critical gap in the current evidence. While projects like Onyx and Gemma have successfully demonstrated browser-based automation and DOM manipulation, the integration of physical hardware control remains an unvalidated extension of current capabilities. The existing repositories focus exclusively on web agent tasks. The specific claim of a complete, self-contained pipeline controlling hardware requires bridging the gap between browser-based inference and serial communication protocols. This step has not yet been fully demonstrated in the standard Gemma 4 ecosystem. Practitioners must acknowledge that true edge autonomy for robotics requires this bridge, a step that is theoretically sound but practically demanding. Running Gemma 4 entirely in the browser shifts the engineering burden from back-end infrastructure management to client-side resource management. You no longer need to worry about scaling servers, managing API keys, or ensuring network reliability. Instead, you must optimize memory footprint and GPU context switching to prevent the browser from throttling the tab. The browser has limits. If the tab goes into the background, the operating system may suspend the process, halting the control pipeline. This exposes a critical failure mode that is typically handled by cloud orchestration layers in standard deployments. To mitigate this, the system requires robust local state persistence and heartbeat mechanisms. The logic for tool calling and state memory must be encoded directly into the model's context window or stored in local index DB. We are trading the infinite scalability of cloud databases for the deterministic, low-latency reliability of local execution. This means the model must be able to maintain its own state across multiple interactions without external memory storage. The system must be resilient enough to recover from a browser suspension or a GPU driver instability without losing its place in the control loop. The implications of this shift are significant. It democratizes access to advanced robotics. You do not need a dedicated server farm to run a sophisticated AI agent. You only need a modern browser and a GPU with sufficient memory, typically between 4 and 8 gigabytes. This allows for prototyping and deployment in sensitive environments where internet connectivity is restricted or prohibited. The security posture is fundamentally improved because the data never leaves the device. The latency is minimized because the processing happens on the same silicon that drives the display. This is not just a technical curiosity. It represents a fundamental change in how we design autonomous systems. The cloud was never the only option. It was the path of least resistance for early adopters who needed to scale quickly without building complex infrastructure. But as the models become smaller and more efficient, and as the web platform gains more computational power, the edge becomes the preferred location for critical operations. The browser is no longer just a display window. It is a powerful, self-contained computer capable of running the most advanced reasoning engines available today. The future of robotics is not in the cloud. It is in the browser. It is in the local machine. It is in the ability to run complex reasoning and control loops without relying on external services. This architecture proves that we can build systems that are secure, fast, and independent. The engineering challenge is no longer about connecting to a server. It is about managing the resources of the device itself. This is the true definition of edge autonomy. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.